Mean free path. So molecules are traveling in straight lines till they run into something. The distance they travel between collisions is called the mean free path. Mean is another word for average, and free path means how far can you go without something in your way. So as the mean free path will decrease as the pressure increases. So pressure increasing, you get the particles closer together, they're going to be running into things more often, and because they're closer. Just an idea of how big the mean free path is relative to the size of an atom. If a nitrogen molecule was the size of a golf ball, it could travel about 40 feet between collisions. So that's quite a long way. You can imagine a gas made of golf balls, and they each travel about 40 feet before they run into anything. There's a lot of empty space in that gas. Here we have an illustration of mean free path. So if we look at this particle and it collides with the wall, so that was a free path there, and it comes over here and collides, and it collides and collides. Here it's mostly bouncing off the walls, but sometimes it bounces off other particles. It's the distance, the average distance it can travel without running into things. So diffusion and effusion are processes by which gas molecules spread out. So there's a subtle difference. So diffusion is where you have a gas that's spreading out from an area of high concentration to low concentration. Effusion is where you have a gas in a container and it's escaping through a tiny hole into a vacuum. So that's also going from high concentration to low concentration, but it's restricted by this container with the little hole in it. The rates of diffusion and effusion are both related to the average velocity. So the diffusion thing, I've got 5 sons, and so you can imagine that there's been a lot of gas passing in my house, right? And they're not even ashamed of it. It's just the thing, right? So if you think about someone farting, right? What is that smell? Why does that smell? Because you're passing gas. It is a gas, and it's a gas that has some nasty organic compound in it that's very pungent, right? So you're over in the corner and you let one rip, and at first the people on the other side, maybe they heard it, but they can't smell it yet, right? But eventually it gets everywhere, right? Why does it do that? Because gas molecules move in a straight line till they run into something. If it runs into the wall, it's going to bounce off and head towards the other side of the room. How fast the gas spreads out to an evenly distributed concentration depends directly on how fast the particles are moving. That's diffusion. If we have gases at the same temperature, the rate of gas movement, the rate of diffusion, the rate of effusion, is going to be inversely proportional to the square root of the molar mass, because the velocity is proportional to the inverse of the square root of the molar mass. So this leads us to Graham's law of effusion. Let's talk about this box first. So here we have this container. It's got a divider in the middle, and initially all the gas is on the left side. There's no gas over here, so that would be a vacuum. And there's a little pinhole. Now we know from experience that if you have, say, one of those swimming donut-y toys, right? And it gets a hole in it. What happens to the air? It comes out. Do you ever wonder why it comes out?
There's pressure.
Well, there's pressure, yeah. Well, what it really is effusion. Although it's not going into a vacuum, but it's going to a place of less pressure. So let's think about what these particles are doing. They're zinging around in here. Now, my brain, just thinking about normal everyday stuff, would think of, well, if there's a hole there, then these guys are all just going to go swoop and swoosh out, right? like letting the pigs out of a pen or something. They're just like going to run out. No. These gas particles just keep doing their thing. They come out when one of them happens to have a trajectory that hits the hole. They're just zinging around until somebody happens to hit the hole. That guy goes through. How fast that happens will depend on the pressure, because higher pressure means you've got more gas particles closer together, more collisions on this wall mean more successful collisions.
So less particles are on that side of the box.
Fewer particles over here. And see, once I get some particles over here, these guys can move to the other side. It's just going to take a while, right? Because there's only a few of them, so they're not likely to hit the hole. How fast the particles are moving also affects how fast the gas effuses. If these particles are moving really, really fast, we've got more collisions and more chance of successful collisions. The successful collision being hitting the hole head on. If you think about balloons, right? So two just regular latex balloons, and you fill one with helium and you fill one with air. Equal sizes, they have the same number of gas particles inside of them. You come back the next day, the helium balloon is going to be noticeably smaller than the air balloon. How does the helium escape from a balloon? Little elves come and steal it during the night? No, latex has little tiny holes in it. And those holes are large enough for gas particles to get through. Helium atoms, hydrogen molecules, oxygen molecules can get through there. But in order to get through there, they have to hit a hole head on. So if I've got helium in my balloon, the helium atoms are moving faster at the same temperature and pressure than the air molecules, the nitrogen and the oxygen, right? And so they're going to have more hits that are successful, so they're going to escape faster. Does that make any sense? This is known as Graham's Law of Effusion, the rate of effusion of gas A divided by the rate of effusion of gas B is equal to the square root of the ratio of their molar masses, but the molar masses are upside down. So it's B on top and A on the bottom. I'll give you this one as well. Just need to know what to do with it. Find the ratio of effusion rates of hydrogen gas and krypton gas. Well, that's going to be that Graham's Law of Effusion. So I'm going to do the rate of hydrogen. It just says the ratio. It doesn't specify what order. I'm going to do rate of hydrogen over rate of krypton. That's going to equal the molar mass ratio, but hydrogen's on top here, so hydrogen is going to be on the bottom over there, and krypton's going to be on the top. Because that's what the law says, the A's and the B's. This should be kilograms per mole, because that's what that funny M is. If I have kilograms per mole divided by kilograms per mole, what happens to the units? They all cancel out. Would I get the same result if I used grams per mole over grams per mole? Yeah, because if I convert from one to the other, I'm multiplying or dividing by a factor of 1,000 on both sides, and that's going to cancel out too. So even though this is supposed to be kilograms per mole, we can use grams per mole because the conversion cancels out. So krypton is 83.80 grams per mole. And hydrogen is 2.016 grams per mole. And I have to take the square root of that. On the 36X Pro, you do the square root symbol first, and then do the 83.8 divided by 2.016 equals. Probably go with 4 sig figs on this. And that's a ratio. It's unitless. The grams cancel, the moles cancel. So what this is telling me is that hydrogen will effuse, escape through a little hole, 6.447 times faster than krypton. Why you would want to know that, I don't know. Any questions?